So today we were going to finish with a theory about fault and fracture reactivation and calculation of stresses. And on Friday we'll do a few problems and we'll finish with the homework, which is going to be due during spring break. No, I'm kidding. It's gonna be after spring break, okay? Yeah, like Friday after spring break. So I'll post that today. All right. So let's see where we are. The last thing we did was to use a Mohr circle in order to calculate stresses for a given orientation. And this is this example over here. And I don't know if you guys were able to solve it or not. Did you guys solve the problem? Kind of? Okay, well, let's walk through that. First of all, what is the stress regime? It's normal, right? Normal faulting because maximum stress is vertical and the minimum principal stress is horizontal. All right, so we're good with that. Then now let me draw the block diagram for that. And I'm going to choose a block diagram because one of the stresses is aligned with, in this case, the east-west direction, so it's going to be relatively easy. So the block diagram for this is going to look something like this. This is my block, where the north is in that direction. And I know that SH mean striking at 90 degrees from the north. So this one is SH min. This one over here is SH max. And this one, the highest, is going to be SV. All right. So I have figured out the state of stress at this particular location. The next step is the fault. And the fault, we see over here, the strike is 0 degrees. So that means that the angle between the strike and the north is 0. So this is just going to be a line which is pointing in direction north-south. And furthermore, this is telling me that the fault is dipping towards the east. So that means that it gets deeper towards the east. So I'm going to choose a plane somewhere over here, and this is dipping 60 degrees. So it's going to be a line somewhere over there, and it's going to be that plane where this is the dip and this is 60 degrees. Okay, so that's everything I need from the block diagram and the orientation of the fault. Now I have all the information I need in order to use the Mohr circle. So forget a minute about if this is normal faulting and what that angle is. Tell me, this red plane that I just drew, it could be a combination of which planes? The plane of SV, the plane of SH min, or the plane of SV and SH max, or the plane of SH max and SH min?
Plane of SV and SH.
These two, right? Yeah. And another option could be it cannot be a combination of any of those. In that case, we would not be able to solve it with this method. And in the homework, I'm going to give you a hint. There is one problem that you're not going to be able to solve with this method. So you need to find which one. I'll just say that cannot be solved with Mohr circle, and that's it. That's the end of the problem. Okay, but this one, it can be solved because this plane is a combination of the plane of SV and SH min. Always try to use the angle from the highest stress to the lowest stress. And that doesn't necessarily mean to SH mean, but could be from SV to SH max, because in this particular case, SH max is lower than SH mean. So that plane is going to be this plane of SV, and because these are the two stresses I'm interested in, that's the Mohr circle that I'm going to draw. Very important when you draw the Mohr circle. Remember that always here we have effective stresses. Therefore, in order to get effective stresses, I have to subtract pore pressure. And actually, I forgot about that. The pore pressure in this example was 10 MPa. I forgot to give you that in the when I presented the problem. So if I know what is the pore pressure, I know that sigma V in this case is going to be 13 MPa. Sigma H max is going to be 10 MPa. And sigma H mean is going to be 3.8 MPa. And for this particular plane, I'm interested in those two, sigma V and sigma H mean. So let's say that this is 10, let's say this one is 5, and somewhere over here this is 15. I know that sigma V is somewhere over here, sigma V, and sigma H mean is somewhere over here, and the Mohr circle in between. Yes, the Mohr circle in between those 2 points, the results from those 2 points is going to be, before guessing, let's do some math, because you're going to have to do it anyways. Remember that for any circle, we can compute what is the center and what is the radius. The center is going to be the average of these two numbers. So in this case, it's going to be sigma V, we said, is 13 MPa. Sigma H mean is 3.8 MPa divided by 2. And that's equal to 8.4, right? 8.4 MPa. And the radius is going to be 13 MPa minus 3.8 MPa divided by 2. And that's going to be equal to what? 4.6 MPa. So, okay, so I go now here to 8.4, which is somewhere over here. This is going to be the center. This is going to be the radius. Wait, I'm trying to make my circle as nice as possible. So if this is 5, this is 10, 8.4, I would say somewhere over there. And this is the radius. I give you a hint to draw circles without any other tools than just your hand. You just draw the radius and then just connect the dots and you'll get an okay circle. Okay? All right, so here we have the center, we have the radius. Before I draw the radius, I'm going to go ahead and use this angle 60. So for this particular problem, I have to calculate shear stress and normal stress for a plane which is at 60 degrees from the plane of SV. Therefore, when I go to the Mohr circle, since I started measuring the angle from the plane of SV, I have to start measuring the angle also from the point of sigma V. 2 times 60 is going to be 120. Therefore, it's going to be a line, a point somewhere over here. And this is 2 times 60 degrees. And this is the radius, and now I can calculate what is tau and sigma n. So I'm gonna let you do the numbers, but I'm gonna write the equations, which we have already written before. Remember that always sigma n at any angle is going to be, let's call this one beta. Is going to be sigma n is the center plus the cosine of 2 beta times the radius, and tau is the radius times the sine of 2 beta. And that's it. So you know what is beta, you know what is C, you know what is R. You can calculate sigma n and tau. Probably the most difficult part here is trying to figure out which Mohr circle to use and which angle to put in here. But once you figure that out, the rest is very easy. Yes? This one? No, because notice that if beta is less than 90 degrees, actually less than 45 degrees, 2 beta is going to be less than 90, and the cosine of an angle less than 90 is going to be positive. So you're going to have to add something. However, when 2 beta is bigger than 90, the cosine is going to be negative. So automatically you will get a negative sign in there. All right, can you guys compute that number, and we'll double check it, and then we'll move on.
Sigma n is 7.9.
Sigma n? 6.1 MPa, and what is tau? 3.9? 3.98? So let's say roughly 4. Something very important that I'd like to mention is, and let's talk about exams. So you already have your grades uploaded in Canvas. I don't know if you saw that, but your grades are already there. And probably if the guys are done with the exams, they're going to bring them now to the class, so you can take your own exam and you can check, compare your solutions with what I'm going to upload this afternoon. And what I want to say about exams is that remember about significant digits. This is something very important in engineering. Probably the precision of our measurements of stress are not very good, okay? So telling me that this is 3.9875, it doesn't tell me much. I know the precision is not so good for stresses, so just providing 2 significant digits may be enough, or 3, that may be enough. That is as important as providing units, and that's something that many of you didn't provide to in the solutions. You got points off if you didn't provide the right units. Okay, so that's the solution of the problem, okay? And this is a relatively easy example. Please go ahead and check the other problems in here. I think I have 3 problems that you can work on, nicer figures too about what I draw in paper. So I believe this is the one we just did, okay? Here is step-by-step the solution, but you have another one in here involving stresses which are not aligned with east-west, and you'll do a few more in the homework, and you will see a solution of those 2. But please go ahead and practice with this, because you're going to have to do it later on. So, yes?
So the one you mentioned,
No, no. This one has a dip of 90 degrees, so it's a vertical plane. Since it's a vertical plane, it's aligned with SV. So it is aligned with one of the principal stresses. If it's not aligned with any of the principal stresses, then that's when you're not going to be able to use this Mohr circle method. So what do you do when you cannot use the Mohr circle method? Well, in that case, you're going to have to use a more complex method that we're not going to go through in class, but you can read about it in the notes, and it's just mathematics. Basically, what we do is, for any orientation of the principal stresses, we can write that in terms of the geographical coordinate system. Basically, what you do from here to here is just what is called a change of basis. And if you remember, in order to change basis from coordinate system to coordinate system, you need what is called a transformation matrix, which is this one. That transformation matrix, here the angles are not okay, because when I convert this to my own editing software to HTML, it doesn't appear. But I'll try to fix it, okay? I'll try to type this equation soon. But basically, these are just these angles alpha, beta, and gamma. Once you change the coordinate system, you calculate this matrix. And once you calculate this matrix, you're going to have this new matrix in the geographical coordinate system. And once you have that matrix, and here you have some examples, then you need to obtain, change it one more time to the coordinate system of the fault. For the fault, you can also define a coordinate system. And in this case, the coordinate system is composed by, the first element is the dip. So remember, first element is always your index finger. Dip, second element is strike, and third element is the normal. So if I have a fault which is pointing down in this direction, this is the dip, this is the strike, and this is the normal. So for any plane, you can define this coordinate system, where remember the strike is on the horizontal plane. Once you have that, you will be able to write these vectors. And with those vectors, you multiply the stress times a vector, and that will give you the normal stresses and shear stresses on any plane. It doesn't matter what this orientation is. Using this tensor method, you'll be able to calculate those stresses. And here, for example, you see the same example that we solved with the tensor, with the Mohr circle method, now solved with this tensor method. And of course, it gives you the same result, but now you have the capability of also solving for oblique planes. And also, you can write this as a script in MATLAB on Python, and it will calculate it right away. You don't have to do any drawings, any nothing. As long as you provide the right orientations of the fault, it will give you those values. If you're interested into solving this particular problem, there is one problem in the homework that it's optional. I'm not going to force you to do it, but if you want to do it and you feel pumped about it, just let me know, okay? And I'll help you to solve it, and to, if necessary, to improve your code in order to get that stresses in the plane of the fault. But to me, as long as you know the fundamentals of why we want to calculate stresses on a plane and which planes are closer to shear, that's what is really important. So let's come back on to why we want to do this, why we want to calculate these stresses. And we already talked about a little bit about this motivation when we talked about reactivation of shear fractures, and also when we talk about placing a wellbore in a fracture formation. We already did that. but I'm going to summarize them here. So this one usually goes by the name stress projection on a plane, and we're going to see three major applications. The first one is about critically stressed fractures. The concept here, remember, is that for brittle rocks, it happens very often that the transmissivity of the fracture is directly proportional to shear stress on the fracture and inversely proportional to normal stress. So that means that the higher the ratio of shear to normal effective stress, the higher the permeability of the fracture is going to be. So how do we recognize these fractures? Basically, we use the Mohr circle, and if I draw a 3D Mohr circle, like this one, now this looks like X more than circles. Let me fix it. I'm very picky about drawing nice circles. Okay, that's a little bit better. By now we know that each circle represents shear and normal stress on the planes, which are combinations of each of the principal stresses. And anything inside are combinations for oblique planes that are not aligned with any of these principal stresses. So anywhere in here, I can get to know what is the normal stress and what is the shear stress. The concept of a critical stress fracture is a fracture in which the state of stress approaches shear failure. And for that, I'm going to add something that we didn't add before. And sometimes I remember one of you asking me about this. What does it mean that some of these points it's above the line? Well, in theory, you cannot be above a shear line. But as you know, for all real materials, their properties are not just a unique number. There is always an uncertainty. There is always a heterogeneity. So in this case, I'm not drawing just one single shear line, but I'm assuming that the rock is heterogeneous and that the rock doesn't have an exact friction coefficient, but it has a friction coefficient that also has some variability. So within that range of variability, there are going to be fractures in this location that are going to be almost a shear failure. All of these fractures are said to be critical stress because they are almost a shear failure. Probably that's something that we cannot observe right away in the subsurface, but we can see that sometimes through permeability and some other times by limiting the state of stress, which I'm going to come back to that in a minute. Why is this important? This is very important because many times with reservoir geomechanics, what we want to do is we want to take advantage of mechanics in order to improve reservoir engineering. So if I have fractures and I can make them more permeable somehow, that's going to be better for increasing production rates, right? The higher the permeability, the higher the production rates. Can you think of any example where you want to increase production rates because the permeability of the rock matrix is too small? I hear hydraulic fracturing. Anything else? So give me more specifics about hydraulic fracturing. Why hydraulic fracturing? Well, this is something that actually many people did not know till 15 years ago or so. Conventionally, the idea of a hydraulic fracture has been always to create a big plane in which you have a high permeability. But recently, we have discovered that, I'm jumping a few chapters here, but we'll come back to where we are, that during hydraulic fracturing, we create microseismicity. What is a microseismicity? All of those points that you see in there are small reactivations of shear fractures. When a small fracture in the subsurface slides because basically it's failing in shear, it emits energy. And if it's reactivating, that means that very likely also its permeability is going up. So here you see all of these are horizontal wellbores. These are fracturing stages. You can't see very well where the fracture is going, but you can see where the fracture is reaching out and where it's changing the stresses to a level that is causing shear in the rock. So this fracture reactivation is very important because it alters the permeability of the reservoir and increases it by adding fracture permeability. And all this cloud of points is what is called an stimulated reservoir volume, because that's as far as the hydraulic fracture reaches in enhancing permeability. And that is directly linked with this. Is directly linked with how many of those points get towards that line. When they get to failing shear, they produce microseismicity and its permeability increases. Okay? This is very important, okay? It's very, very important, and I hope you remember that. Probably I'm gonna ask that again in an exam. But it is a very, very important concept. So I was thinking the other day about a class I took once in thermal. I don't know, have you guys taken thermal already? Yes. I don't know, let's not say anything. I'm not asking you to judge thermal, okay? But it's my own experience with thermal. I remember the class, was not very good because the professor was showing like so many materials, so many charts. I didn't remember anything. Even up to today, I have a sort of a post-traumatic stress disorder when I think about thermal, because it was so much stuff that I don't remember anything. The only thing I remember is the second law of thermodynamics, but because I remember that from somewhere else. But I come from this class that my objective is not to bombard you with lots of things, but it's that you remember very simple and important concepts. And this is one of those, okay? This is one of these very important things that you have to remember. Shear fracture reactivation helps permeability, and you can also map it with microseismicity. I'm going to come back to microseismicity also later on. Probably, I don't know if there is any of you from Oklahoma, that this is a big issue also in Oklahoma, or it was a big issue, now it's relatively solved. It's a big issue in Canada too. All right, so one of the applications is enhancing permeability through taking some of these fractures to shear reactivation. The second one, it's we go to one step further in size, and now it's not about small fracture reactivation, but it's about fold reactivation. So some of these fractures that are reactivated during hydraulic fracturing, they may be like in the order of several feet of length, the fracture as it reactivates. When we talk about the fault, we talk about hundreds of feet or even more. So we're talking about a large plane. But it's exactly the same concept. If we have a fault which is oriented at a given angle so that if we change the state of stress and take it closer to the shear failure line, before I tell you the solution, let me ask you that. Let's say that we have the current state of stress. We know what is effective normal stress, effective intermediate stress, and minimum effective stress. How can I change effective stresses in the subsurface? Decreasing pore pressure. Well, decreasing pore pressure, what is going to cause? If you lower, remember that effective stress is equal to total stress minus pore pressure. So if you decrease the pore pressure, what happens with effective stress? It increases, right? So decreasing pore pressure, as done with depletion, I'm going to make it a little bit more accurate. It actually moves a little bit like that. Depletion, this is what is called a depletion path. The three circles are going to move towards the right. Yes?
But you don't want to cause the compression failure line.
Say again?
Compression failure line. There was an arc that you...
Well, sometimes you can. If you do too much depletion, and we're going to see later on that when we get into other problems related to reservoir geomechanics, if you go too much into the right, you also cause compression failure in the rock.
Is that okay?
Sometimes okay, but sometimes it may not be okay. There is a balance of how much compaction you may want to have. But okay, if you decrease the pore pressure, you go through a depletion path. On the other hand, sometimes you may want to increase the pore pressure. Why? Because for pressure maintenance, for water flooding, for storing fluids in the subsurface, you may increase the pore pressure. And if you increase the pore pressure too much, you may run into this circle bumping into the shear failure. And when that happens is when you get full reactivation. And many times you do not want to do that, because that's what sometimes causes not microseismicity, but causes macroseismicity. So you have to be very careful for that. And more or less the maximum or the minimum, not the maximum, the minimum pressure that you need in order to cause that shear full reactivation is going to be equal to the distance between horizontal distance between the Mohr circle and the shear failure line, which in this case, is going to be that distance. Notice that the point with the maximum shear to normal stress ratio is the one the closest to the circle. This one is further away. This point over here too is further away. The one closest to the shear line is that one. So let me show you an example about full reactivation. Are you guys familiar with CO2 geological storage? So CO2 geological storage is basically a technology that now is being pushed forward in order to decrease the carbon emissions from burning fossil fuels. And in order to do that, you take carbon dioxide from power plants, and then you pump it towards deep formations and just leave it in there. But notice in this case, if you're injecting something, you are increasing the pore pressure in the subsurface. And in this particular example, this was a case of CO2 injection in Illinois. And after pumping a significant amount of CO2, they started to observe microseismicity. So what you see here, this is a top view, okay? This is a top view, and all of those are events of microseismicity. This is the y-axis in feet, north-south, east-west in the x-axis. Question: what kind of faults are those? Notice that here you have help from what is the maximum horizontal stress. This is the kind of questions that I expect you to understand from after solving the homework, after reading the notes, that you're able to interpret this kind of data. If you are in a meeting in the future and you're exposed to some of this data, you're able to understand that right away. So again, this is a top view. This is the direction of maximum stress. Notice how the microseismicity aligns in a preferential direction. So for some extra points, who can tell me what those faults are? Most likely. No, raise your hand so I can see. Okay, you already have points.
Is it normal fault?
Why normal fault?
Because to me the fractures are like this, so the azimuth is parallel with the maximum horizontal.
So,
which means that it would be the two strongest fault, or the weakest, the smallest amount of effective stress would be the minimum, and the highest would be the vertical.
okay. So vertical, remember, is
Depth.
right.
Should be depth. Well,
Yeah.
into the screen would be vertical.
Yes, correct. So notice how those microseismicity points show up there. They basically align along the strike of the fault. This like that, right? And what we are seeing over here is, again, the strike of those faults. Those points allow you to see the strike. And if this is the maximum horizontal stress, this one has to be the minimum because it's perpendicular to that. And because they're aligned in this orientation, it means that very likely these ones are normal faults, which are either like these planes, or like that. We don't know in this case, but these are planes like that will injection of, in this case, carbon dioxide, they get reactivated. Okay, did you guys all understood what's going on in there? So, let me come back over here. Fault reactivation is a big issue, and especially for unconventionals, it's very important to understand this problem for water disposal, for produced water disposal. Second application, and let's go to the third one. The third application is the determination of, you could call it limits or bounds of horizontal stress. Okay, what does this mean? We are saying that if we increase stress too much, effective stresses too much, if the diameter of this Mohr circle gets big enough, it's going to run into the shear failure. And it cannot grow any bigger than that. And what that also means is that depending on what is the value of the vertical stress, there are limits for horizontal stress. So remember the case that we were doing for thrust fault, the one of the dinosaur. We were saying that if eventually you push too hard in lateral direction, at some point the crust is going to break like the thin crust of the dessert of creme brulee. Same thing. So if it breaks, it means that at that point it's not taking any stress higher than that. What this also means is that when we are computing horizontal stress, and let's say this is strain, this is stress, there is going to be a range in which we can calculate what is that horizontal stress based on some sort of stiffness modulus and the tectonic strain. You guys remember this equation? The full equation is sigma h is this sigma b plus the constraint modulus sigma h max, so on. Okay? So that is this region where the stresses are proportional to a tectonic strain. But as we're saying, there's going to be a point in which the subsurface is going to break, and we're going to have faults and faults, and at that point the stress is not going to go any larger. And at that point we're going to assume it's going to plateau, and at that plateau we're saying that the maximum effective horizontal stress is going to be equal to this friction parameter Q that depends on the friction angle times sigma 3. So if we know either this one or that one, and we know also the friction coefficient, we can tell what those stresses are. For example, let's assume a case of normal faulting. What is, in normal faulting, what is sigma 1? SV, or let's call it sigma V. And what is sigma 3? Sigma H mean, right? So what this equation is telling us is that if we know what is the value of sigma V, which we usually no, because it's relatively straightforward to determine. We can determine what is going to be the minimum value of sigma h mean. So sigma h mean cannot be lower than sigma v divided by q. Sigma h mean cannot be 0, because if it's 0, it's going to be already there's going to be some fault around that's going to be failing. And basically, if we want to use this equation to calculate minimum horizontal stress, everything you have to do is go to a site that in this case, let's assume is normal faulting. And for this particular location, we know that there are normal faults. And if there are normal faults, that's when we can apply this equation. If we know what is sigma v, we can calculate sigma h mean. And I think I have an example about that. Oh, okay. So it's just a generic example. So the first thing that you do, if you know what the depth is, you can calculate SV. We know how to do that very well, right? And most of you did very well on calculating SV in the exam. There were just a few minor mistakes, and probably 75% of you did not calculate what I was asking you in the last point. I was asking you for total horizontal stress, and many of you calculated effective horizontal stress. And I underlined total because usually in the field we cannot measure effective stresses. We measure total stresses. So for that case, you needed to calculate the total horizontal stress. Okay, let's come back to this. You have vertical stress, and also we know that we can calculate pore pressure as well. If we know these two, we know what is the value of effective vertical stress. What this equation is telling me is that the minimum effective horizontal stress is going to be a fraction of sigma v. Let's say that q is equal to 3. Okay? I'm assuming it can be different than that. So what is going to be the value of the minimum horizontal stress? Effective. It's going to be a third of this. So a third of that, somewhere over there, and proportionally it's going to be somewhere over there. So this is sigma h mean, and this line is sh mean. So if you want to calculate that numerically, basically the first thing that you have to do is compute the total horizontal stress, total vertical stress, pore pressure, effective vertical stress, the same thing as we did before, and then just use this equation, and you can tell what the value of the stress is. Amazingly, this equation works very well in many places. What tells you that in many places around the Earth, the crust is almost at failure in many places. And that's why this equation works very well. So here's Jeffrey, and he has your exam. So just stop by, talk to Jeffrey, and pick up your exam, all right? See you on Friday, guys.
Welcome.